Alright, hey guys, welcome to the series on projectile motion. In this video we focused about a few critical concepts, just explaining a couple of the formulas and where they tend to come from, other than the ones that we've already spoken about. Because in the instance on this particular video series, we're looking at changes in both landing and release heights. So there's a formula in your book, right, that tends to look something along these lines and says that the time that a projectile typically spends in the air is equal to 2 v naught sine theta divided by gravity, right? This formula can only be used when the landing and release heights are exactly the same, right? So can only be used when landing and release heights are the same. Alright, so what happens in the case where the landing height is not the same, right? And you've got a particularly horrible looking formula that looks something like this, and it says that the time, in this case, that the projectile spends in the air is equal to v naught sine theta plus the square root of v naught sine theta squared plus 2gh and all of that over g. Okay, well, you might be surprised to find that I can still use this particularly horrible looking formula in the case where release and landing heights are the same. It just tends to simplify to this one. So in the case where release and landing heights are the same, the change in height is 0, right? So this height component will be 0. So this delta h would just be 0 since there's no difference between landing and release heights. So in all of this, this would tend to go to 0. The square root of something squared will tend to be itself. So this formula would just look like this, v naught sine theta plus another v naught sine theta over g. And since I've got two of the same values, I could just add them together to v naught sine theta over g. Right? So you can see it's the same thing, but obviously this becomes a lot more useful when there are changes in release and landing heights, and it's going to factor in this change in height in this formula over here. Okay. Again, even this simple formula tends to also come from one of our fundamental formulas, which says that this change in height is equal to some initial velocity times time plus 1/2 not g but at squared, right? We've seen this come up time and time again. Since we're talking about time in air, and time in air is proportional to the vertical velocity, we just look at the y-plane motion, right? Which in essence will then tell us that the change in height vertically is equal to the initial vertical velocity times time plus 1/2 the acceleration in the y direction times time squared. Alright, so from earlier videos we know that the initial velocity in the vertical direction is equal to the initial velocity times the sine of the angle. In other words, the vertical component of this initial velocity is defined by this particular formula over here. And we also know that the acceleration in the y direction is just negative g. Remember that our particular convention is anything going up and to the right is positive, so anything going down and to the left is negative. So since acceleration vertically is the downwards acceleration of gravity, it is g, but because it's going down it is negative g. So if I replace this convention in here and the fact that there's no change in vertical displacement, if I look at the same landing and release heights, this would tend to 0. So I'm just left with v naught sine theta times time minus 1/2 gt squared is equal to 0. When I bring this v naught sine theta times t over to the other side, I'm left with negative 1/2 gt squared is equal to negative v naught sine theta times time. So I've got a negative on both sides, so they tend to cancel each other out. So I'm just going to remove them to make the math a little bit easier to deal with. I'm going to multiply both sides by 2 to get rid of this half. So gt squared is equal to 2 v naught sine theta times time. I've got a t on both sides. I'm going to divide everything by 1t. So that's going to get rid of this t over here, and it's also going to decrease this by 1. So then I'm sitting with gt is equal to 2 v naught sine theta, right? So time on its own then, if I divide both sides by g, is 2 v naught sine theta over g. Okay, so you can see that that's the formula that I was talking about earlier, the one that you'll see in your textbooks, and we can see the slightly more complicated version of it pertaining to discrepancies between release and landing heights. Alright, so where does this horrible thing come from? So this is when differences in release and landing height are observed. Where does it come from, right? Just to keep making sense of everything that we're seeing. Everything comes from a reason. So in your guys' math class, you guys would have most likely been exposed to parabolas, right? Parabolas have this same kind of curvilinear function that projectiles tend to have. So we could probably use the mathematics behind parabolas in order to solve for projectile motion. Traditionally, we'd have x and y and x axis, or x and y axes, the y axis being your vertical, the x being your horizontal, and a parabola is generally governed by this simplistic formula, or this generalized formula, which says that the equation describing this parabola is equal to y equals ax squared plus bx plus c. Okay. So a formula that may describe this one would typically look something like this. Y is equal to, let's say, negative 4x squared plus 21x minus 5. Right? So whenever I see a negative number, it would be this kind of frowny face. And if it's a positive number, the parabola would look something like this. But we're not going to talk about those ones for now because we're interested in projectile motion. Okay, so you can see this negative 4 is this generalized a here. It's the number in front of the x squared. This 21 is the b. It's the generalized number in front of the x. And then this minus 5 is the c, right? The number at the end that's not related to any x's. And it's saying, like, I could find the x coordinates whenever y is equal to 0 by utilizing this quadratic equation over here that finds the roots of x, right? And then you can see it's negative b plus minus b squared minus 4ac over 2a, which looks terrible, but these a, b's, and c's come from this equation, right? The a, b, and c that I technically have, I can just plug into this and I would find out what x is. So we could try that quickly just to kind of like prove it. And I would say that y is equal to, sorry, not y, that this x is equal to, it's minus b, so it's minus whatever the value of b is, which is 21, plus or minus, which is where the two different roots will come from, 21 squared, right, it says b squared, minus 4, whatever the value is of a, in this case it's negative 4, times whatever the value of c is, which is negative 5 in this case. And all of that divided by 2 times a, which is negative 4. Alright, so this would be negative 21 plus minus the square root of all of this junk in here, which is equal to, let's just do it in the calculator quickly, 21 squared minus 4 times negative 4 times negative 5, which is equal to 361. So I just got to find my cursor for a second. 361, and all of that over negative 8. So I'd still have negative 21 plus minus the square root of 361 is equal to 19. And all of that over negative 8. So I have two options here. One is going to be negative 21 plus 19 over negative 8, and the second option is negative 21 minus 19 over negative 8. So let's just do this one. Negative 21 plus 19 should give me negative 2. So negative 2 over negative 8, negatives cancel and I get a quarter, right? This one over here, negative 21 minus negative 19 is negative 40 over negative 8. Again, the negatives cancel and 40 divided by 8 is 5, right? So in essence, it's telling me that this x value over here is 0.25 or a quarter, and this x value over here is a 5. Okay. But notice in the earlier equation, on the previous page that we looked at, notice how these two equations look very similar, right? In most of our parabolic flight paths, yes, we have some kind of vertical motion, still denoted by y, but this x just seems to be replaced by a t, right? Time. So what is the change in vertical motion relative to time? Looks very, very similar. So I have this equation that tends to look like this. Remember our fundamental equation that our change in vertical displacement, if we look at our vertical values, is equal to v sub naught y times time plus 1/2 the acceleration in the y direction times time squared. Looks kind of similar to this, right? So if I had to rearrange this bottom equation to look a little bit more similar to that, I would say it's 1/2 acceleration in the y direction times time squared plus v naught y times time, and then this minus delta s comes to this side is equal to 0. So notice now how this looks very, very similar. I have some t squared instead of a x squared. I have some t instead of a x, and then I have some constant value instead of a c, right? If I just replace the values that I already know, ay vertically we denote typically as negative g, and v sub naught y is equal to v sub naught sine of theta, right? So 1/2 times negative g would be negative 4.905. Right, let me do it differently. I don't want to plug the values in quite yet. This would simply be negative 1/2 gt squared plus v sub naught sine theta times time minus delta s, right? Notice that this is equivalent to our a that we were talking about earlier. This is equivalent to our b, and this is equivalent to our c. So if I wanted to find t, I could use the same quadratic equation except replace x with t. So it would look something like this. T is equal to minus whatever the b value would be, which is v sub naught sine theta plus or minus v sub naught sine theta squared minus 4, and a in this case is 1/2, negative 1/2 g, and the c is equal to negative delta s. Let's extend that out a little bit, and then all of that over 2 times whatever a is, which is negative 1/2 g. Okay, so 4 times a half is negative 2, and all of that would just simplify to the following: negative v naught sine theta plus or minus v naught sine theta squared minus 2 g and delta times delta s, all of that over negative g. So 2 times a half is just negative. So you can see here, instead of going with the negatives, we just went with the positives, but in essence that's where this formula comes from, right? Delta s is just height, v sub naught theta is just vertical velocity, no surprises there. G is just gravity. So that's in essence where that formula comes from, right? So now that we've explained that, we're going to put all of this stuff to use. So the next video will go through a specific example that will just allow you guys to practice that a little bit further. Okay, so hopefully that makes sense, and I know it's a lot of mathematics. I'm not going to ask you guys to derive any of this. All I wanted to do with this video is to show where these formula comes from. They're in your books, and a lot of people don't understand where the heck and why the heck am I using these formulas. But in essence, it all comes back to parabolic motion, and we can use the equations that describe parabolic motions in projectile motion. That's it. Straightforward.